What happens when AI learns to improve itself, not just faster, but smarter, more locally, and in real time? In this episode, we explore three striking frontiers: test time scaling that boosts scientific discovery through smarter evaluator loops, tiny language models that deliver instant on-device replies before the cloud finishes the thought, and a new training method that restores self-improvement in large reasoning models without losing diversity. From quantum circuits to math Olympiads, the results are reshaping what efficient, adaptive AI can do. Let's explore the first paper: evaluation-driven scaling for scientific discovery. Evaluation-driven scaling for scientific discovery introduces Simpletes, a test-time evaluation-driven scaling framework that reallocates evaluator queries across three axes: global width C for parallel trajectories, refinement depth L for iterative feedback, and local sample size K for best of K commitment. The core claim is that scaling the evaluator loop, not only reasoning tokens or agent turns, is a stronger driver of scientific discovery when a surrogate evaluator V provides dense feedback. Using open source GPT-OS 20B and GPT-OS 120B, Simpletes reports state-of-the-art or ties state-of-the-art results on 21 tasks across 6 domains, while matching or beating frontier model baselines and more complex systems such as Alpha Evolve, Open Evolve, Theta Evolve, Shinka Evolve, TTT Discover, and K-Search. The strongest gains are concrete. Superconducting qubit routing reduces added CNOT overhead from 60,189 to 45,441 on IBM Q20, a 24.5% drop versus Lightsaber, and 21.7% versus Saber. Zoned neutral atom compilation lowers geometric mean execution time by 33.2%. The lasso path solver is 2.17 times faster than GLMNet and 14.08 times faster than sklearn. Trimol on H100 reaches 1.122 milliseconds, outperforming prior AI kernels and generalizing to A100, H100, H200, and MI300. And scaling law discovery improves average test R squared to 0.674 versus 0,femsu 2 for SLD agent. In combinatorics, it finds a new sum difference score of 1.143975, 8.03% above the best human result. And in biology, it raises single-cell RNA-seq denoising to 0.74 on tabula muris. The paper also shows trajectory-level post-training on successful Simpletes rollouts, improves both in-domain and out-of-distribution discovery, and explicitly analyzes reward hacking modes in surrogate evaluators. Let's explore the second paper: micro-language models enable instant responses. Micro-language models enable instant responses proposes commit and continue generation for edge devices. An 830M parameter decoder-only micro-LLM emits the first 4-8 words of a reply on device. Then a cloud LLM completes the answer from that prefix, masking cloud, round trip, and queuing delay. The models are trained from scratch on 485B pre-training tokens drawn from UltraChat, MOS, and Instruction, Merge, Set, plus 323 4M supervised fine-tuning tokens. Using a 12,288 token BPE vocabulary, GPT-style transformers with rope, RMS norm, swigglue, grouped query attention, and tied embeddings. Across 5 variants, the best local model is 2885M parameters. In zero-shot LM eval harness on HeliSwag, PIQA, BullQ, Arc Challenge, in OpenBook QA, it reaches 0.39 overall, outperforming several 70M, 256M baselines, and matching or exceeding small instruction-tuned models on dialogue-style quality metrics. For collaborative generation, the cloud is instruction prompted as a continuator rather than a respondent, enabling mid-sentence handoff and structured recovery via explicit correction, natural recovery, or humor-aware recovery. User studies with 15 participants found the stitched output was preferred over standalone Quinn 323 FLAF BA22B in 28% of comparisons, tied in 49.3%, and prefer standalone in 22.7%. 77.3% were tie or prefer collaborative. The preferred recovery mode was natural recovery, 44% ranked first, followed by humor-aware recovery, 36.7%, with explicit correction least preferred, 19.3%. The optimal prefix length was 8 words. 4 words yielded the best average in most settings, while 16 words degraded semantic coherence and increased handoff correction rate from 3.7 to 8.4% at 4.8 words to 16.4% at 16 words. On an Orange Pi 5, the 28M microlem achieved 45 milliseconds time to first token, 3 milliseconds first token decode, and 55 milliseconds for 4 words, with 4.3 times higher end-to-end throughput and 4.5 times lower energy per token than small LM2, 135M. Instruct. Let's explore the third paper, Tempo Scaling Test Time Training for Large Reasoning Models. Tempo introduces an EM-formulated test time training framework for large reasoning models that breaks the plateau of self-rewarding TTT methods such as TTRL and EMPO. The key novelty is alternating policy refinement on unlabeled test questions with periodic critic recalibration on a labeled dataset, rather than relying on fixed self-generated rewards. The authors show that prior methods are effectively incomplete EM procedures that omit the E-step, causing reward drift, overconfidence, and diversity collapse as the policy changes. Tempo restores the missing posterior estimation step by training a critic on labeled data with token-level MSE supervision and using its calibrated value estimates as quality-aware rewards for policy gradient updates. This yields a tighter elbow and sustained improvement under additional test time compute. On AME 2024, OMO 37B rises from 33% to 51.1%, and Quinn 314B from 42.3% to 65.8%. On AIM 2025, the same models improve from 26.3% to 37% and 37.1% to 44.6%, respectively. Tempo also preserves diversity. Unlike TTRL, which degrades pass-at-K over training, Tempo maintains high pass-at-K on challenging math benchmarks. The method generalizes beyond mathematics, with large gains on BBH, AGI, eval, Zebra Logic, and GPQA Diamond, including plus 21.4 on BBH and plus 24.5 on AGI eval for OMO 37B. Ablations confirm that freezing the critic causes plateauing, while supervised continuation on the labeled set saturates immediately, establishing that periodic critic recalibration is essential for scalable test time self-improvement. That's a wrap on today's AI paper highlights. Thanks for watching.